Welcome everyone to our next session by Adam Sandman. Unfortunately, he's not here today, so we have a recorded session for you. But let me shortly introduce him. So Adam Sandman was a programmer from the age of 10 and has been working in the IT industry for the past 20 years. And currently, Adam is a director of technology at Inflectra Corporation, where he's interested in tech, business, and enabling people to follow their passions. So for the presentation, we have several takeaways. You will learn about the main concepts and design patterns in software architecture. You will be able to access and evaluate the key areas of technical risks in system. And you will have the tools to create a test strategy and plan that mitigates these risks. So, and now let's jump to the talk and enjoy everyone the session. If you have questions, you can answer them. You can ask them directly to him. You can find him on LinkedIn. I will post the link in the chat.
Hi everyone, my name is Adam Sandman and I'll be talking today about software architecture, where the bodies are buried. So first of all, a little bit about me before we get into the presentation. I've been a programmer since the age of about 10, so that's quite a while ago. We won't go into how many years that is. And I've been working professionally in the IT industry in the United States for the most part for the past 23 years. And currently I'm the Director of Technology at Inflectra. We're a software testing company based in the United States. And I have lots of interests around technology, business, innovation, and I love technology as a kid, and I love it as an adult, and how we can use technology to improve our futures and harness technology to have great outcomes, and hopefully avoid things like the Matrix. If you want to get in touch with me, I'm on Twitter and increasingly probably more on LinkedIn these days. But either channel you can get hold of me. Just send me a DM or a chat. Okay, so more importantly though, what are we going to be talking about today? Well, we'll be talking about software architecture. And you might be thinking, well, hold on, isn't this a software testing conference? So why are we talking about architecture? Well, one of the key reasons will be we want to understand how you can use knowledge of software architecture to assess and evaluate risk in a system to help and improve our testing and the test process. So if you like this presentation, hopefully you will take away what is software architecture? How can it help you inform the risk in the system you're testing? But also it should help you understand the test strategy and plan out, based on what you know of the architecture that's being tested and what changes have been made in the architecture, what is a good test strategy and a good test plan to mitigate those risks. And at the end, we'll talk about a couple of case studies from our own internal experiences where we have not fully understood the architecture and the risks involved, causing lots of frustration and miscommunications. And hopefully you will learn from those two case studies to improve your process. So we're going to be talking about architecture, but where are the bodies? And I call it that because software architecture is often a mystifying topic. And if you don't understand it, what often happens is bugs and errors and issues seem to appear from like the zombies from the undead, from the gravestone. Out of nowhere, out of a seemingly calm and beautiful green pasture, the undead will rise. Similarly, from a beautiful and well-functioning system, out of nowhere, with just one small change, suddenly all these issues can occur like the undead. And so that's what gave me the idea for the talk, that if you don't understand software architecture, seemingly random, unexplainable things can start happening. But once you understand software architecture, it's amazing how much easier it is to understand why something happened and why something small that was changed results in a lot of bizarre and big interconnected or maybe not seemingly interconnected issues. So in the agenda, first thing I want to do is give a little bit of a background on software architecture. Why is it called architecture? How has it evolved over the years? And why is it important to you? I'm then going to be talking about how basically software architecture informs testing and development. And I want to address very specifically the agile concept of refactoring. Refactoring is something that really has come about since the adoption of agile methodologies about 20 years ago. I want to help you identify where areas of where there might be risk in the architecture. I want to show you cases where things may be connected, things are not connected. Is everything connected? It's a very metaphysical question, but actually in software testing and development, there's lots of important relationships that need to be understood because a lot of things are connected, but sometimes things are not. And then I've got two case studies of our own personal experience of dealing with this. So first of all, I want to talk about a little story, which is a real story we actually had, but it's based on something that happened in our office, but the names were changed to protect the innocent. When Danny and Tina got into a fight, or almost got into a fight, and what we learned is that a misunderstanding and miscommunication between them could have caused a major blow up on the team and delayed the release. And if we had spent some more time understanding the architecture, particularly if our developers and testers had worked to educate each other on how software architecture that they were working on plays a role in the process, I think they would have had a much greater understanding at the beginning and less issues. So what was going on? So we were working on our help desk tool. It's going to be one of our case studies later. And our help desk tool has lots of good practices built into it. We're using Agile, we're using DevOps. So we've got developers writing code. It's a C# application, JavaScript application. Stuff's being coded into Git and committed into Git. We're building continuously using Jenkins. We've got an automated set of unit tests. We've got manual testers doing exploratory testing. We've got some manual scripted tests. We've got some automated UI tests. So a whole bunch of good testing practices are built in here. Coding, building, integrating, unit testing, API testing, and then some exploratory testing, plus some traditional manual testing. And the application looks like that. So it's all good. What happened next? So that morning we came in, the build had finished, and Tina, our tester, was just doing some initial testing. And suddenly she said, well, I just tried the first thing and it broke. And yet Danny, the developer, had marked some bugs as fixed in Git and in our issue tracking system. And she was upset that, why don't you test anything before you commit it? Typical of you developers, you never test anything, you just commit it and walk away and leave us testers to deal with it. And Danny, our developer, was like, Tina doesn't understand how the system works. I fixed everything. It should have worked. And in fact, on my machine, it did work. So it's not my fault. Grr, what's going on? So that was the problem. Now, the question is, how does this play into software architecture? Okay, sounds like just a miscommunication. Well, we'll find this more when we go back to that case study. So we'll hold on to that and we're going to come back to it. But by having a conversation with Tina and Danny, we actually got to find out that software architecture was the root of cause of this issue and of this problem. And in fact, this is what inspired me to create this presentation, because I realized that when we spent some time with Tina and Danny going through the architecture of our system and explaining how it all fit together, there was a much greater understanding, and Tina had an epiphany going, oh, I see now. And Danny's like, oh, I see now. And so it really helped have a communication and understanding. So that's why this is such an important topic. But we're going to come back to that later. First of all, software architecture history. So architecture in software is called that because it often looks like a building. In buildings, if you've ever imagined being an architect in real life, and I've never really done that, but if you had, you imagine you have a foundation, you build on top of the foundation, you build the walls, you build the rooms, and on top is a roof, and there's your building. So software architecture is sort of the same way. Simplistically, software architectures are typically built up of three main layers, particularly applications that we'll be using as a human that we interact with. It's obviously simplified because you may have things like APIs, and each of these layers could contain multiple sublayers. But broadly speaking, we say there are three software layers in software architecture. The bottom layer is the data management. So where is the information being stored? Traditionally, it might be like a relational database on a hard drive. In the olden days, it could be tape storage. It could be magnetic storage of other formats. Nowadays, it could be flash memory. It could be a relational database running on that. It could be a NoSQL, object storage, flat files. All of that, that's all data management. It's managing where is the data, how is it stored, how is it maintained, so that when you put data into it and then put data out of it, you have a reliable way of retrieving and creating and updating data. It's got high integrity, it supports multiple users, all those important attributes of it. But ultimately, its job is to take data, store it, and give it back to you, and make sure it doesn't disappear in the process, doesn't change erratically, make sure there's an audit trail, you can undo things, all of those aspects. The tier then that's put on top of that is, well, I've got all this great data, but what do I do with it? So it's called the application layer or the business logic layer. At the very least, its job is to get the data out and do something with it. That's the simplest thing, which will be retrieving some data and putting data in. It's the layer that does that in, retrieval and creation from the data storage. In many cases, it would often do processing on it. So for example, it might validate the data, it might do calculations on it. If you're going to create a new purchase order in a system or a new airline reservation, it may do some other things at once. It won't just store the reservation. It's also got to check, are the flights available? Is there enough availability for that particular seat? Is the seat available? Is it the right class that you paid for? There's a lot of stuff going on that's not just data processing, it's business processing and logic. It's taking the data elements from different parts of the data management tier and doing things with them. That's the business layer. In theory, most of the hard work should be done there. There's a fair amount also being done in the data management layer. And the idea is that that business layer is independent of retrieving or doing something with the data that someone can see. So if I go to a web page and I'm going to receive this data, or if I go to a mobile app, or if it's an API that someone else is accessing, those are all different ways of retrieving and visualizing the data. And that top layer we call the presentation layer. Its job is to take the data that's been transformed and manipulated by the business or application and display it in some fashion. And traditionally, we thought of this as something that we display to a human being on a screen or a device. Nowadays, it could also be, you can argue, the API layer that if a machine is consuming it. So if it's a Internet of Things type of application, or it's an API service, maybe the presentation layer is not actually for humans, it's for some other computer. So you could argue that's sort of a pseudo presentation layer. But traditionally, the presentation layer, business layer, data management layer. And depending on when you got into computers, if you started out in the 1970s, it looked a lot like this. It was a mainframe application that the text-based interface was all you had. It was called a green screen because it was originally green text on black. Some of the later ones had some color as well, where you could have highlighting. You've got some red and other colors. But traditionally, it's a text-based, column text and column-based user interface on what's called a terminal. And it was called a dumb terminal or a thin client because all that screen could do is get text given to it and would display it. And if you typed it on the keyboard, it would send the keystrokes into the server and it would do all the work. So the terminal, the green screen terminal, really didn't do very much. It was literally just displaying text. And so and that was on the terminal that was sat next to you. And then miles away in a data center would be the mainframe server, and it would receive the text and send the text. Everything in terms of rendering and designing the layout of the screen was all done on the server. Any logic around taking the data and doing something useful with it, if you were going to make a reservation, it would be checking the availability. If it's a banking app, it would check there's enough funds in the account. All that stuff's done on the server. That's your business logic. And then data storage. In those days, it was probably magnetic tape, maybe disk. Probably not floppy disk, probably not even a hard drive. It was those disk platters, if you've ever seen pictures. And some examples would be, IBM AS400s, IBM 360s. And guess what? These are still in use today. If you're booking flights for Delta, I believe they're still using some of these machines. Many banks still use these types of application because they are reliable. They don't break. Core banking apps are very hard to build. The testing is incredible. If it isn't broken, don't fix it. And so there are a lot of applications in use in business that still use mainframes, still use COBOL, still use this architecture. The one problem with this architecture was that all the processing had to be done on the server. It meant it was slow. It meant you couldn't do very much. And so in the 1990s, early 90s, late 80s, you started moving towards what was called thick client or client server. That's in use today. If you go to many stores where they have point of sale systems or warehouses, they'll have things like Microsoft Dynamics, Oracle E-Business, SAP. Those are thick client apps where you have a Windows, it's mostly Windows, but it could be Java, Windows type app running on your desktop, and it communicates with a remote server. So you've now pushed, if you look at the layers, we've pushed the business logic and the data storage into the application server, but our local Windows desktop computer is doing quite a lot of the work. It's drawing the screen, it's drawing all the objects you see. It's also doing quite a lot of the business logic in some ways. It's doing some of the validations, some of the processing. A lot of that is being done on the desktop computer that you're running. So it's more scalable. In fact, in some very extreme cases, only the data storage is remote. The entire app is on your machine, and the application server is just doing data storage. And some apps are written that way. So you could have all the logic on the desktop and almost nothing on the server. You could have very little logic on the desktop and a lot of it on the server. So the size of those two blue blobs that we have the business logic in, the ratio between what's local and what's remote has varied over time, depends on the application, depends on the network, and a variety of other factors. But that's the design of thick client. And then in 2000, we have the internet revolution. We have the first web applications. Originally, they were thin client web, we call them, old school web, or web 1.0. You have a web browser. The web server would send documents that could be static, could be dynamic. They're sent to the web browser. The browser basically has a very little functionality in it. in its earliest form, it literally just takes pages of text and a markup HTML, displays them, might with JavaScript do some animations or some basic validation, but almost nothing is done on the web browser apart from displaying the page. Traditionally, the web server sends the content, sends the pages. When you push a button to submit something, it sent it back to the server. All that's being done on the server. And so in that case, you have a thin client application where you have the web page is constructed on the server. It's sent to the web browser. Any logic is done on the web server. Data storage, it's probably a relational database at this point, Oracle, SQL Server Sybase, depending on what era we're talking about here. And on the technology stack, you're probably using HTML, server-side rendering, and things like ASPX, Active Server, JSPs, PHP, Perl, those kinds of technologies, Web 1.0. And now we move into the current day, and obviously there's different flavors of this. I'm just picking the main sort of epochs, the modern internet application era. And we've actually kind of gone back to a bit of client server. So it's a sort of a hybrid model now between web browser and mobile devices and client server sort of feeling. So on the web browser side, for the most part, we're not installing apps on our desktop machines anymore. We're using web browsers that load up the app, and as well as uploading in the pages and the data, they also have the JavaScript frameworks like React or Angular, which effectively are an application resident in the browser. The logic is being done in the browser on those technologies, and it's communicating with the web server. That web server is both sending potentially the page template, but also much of the rendering is being done on the browser. But all the data back and forth through Ajax is being done through web services from the web browser, from the web app, directly back to the web server, where there's additional logic and there's data storage as well. Exactly, how much is being done in the browser versus how much is being done on the server, again, depends on the application, depends on security. Typically, anything done on the web browser has to also be done on the server to avoid people spoofing and trying to do hacking. So even if you validate something on the web browser that seat's not available, someone could spoof the request. So you have to do the check also on the server. So you're doing a lot of stuff on the browser for responsivity and to improve the user experience. The logic on the server has to often be redone just to make sure that no one's trying to break into the system or do things they're not supposed to. We also have mobile devices, and mobile devices, they're native apps, so they are more like client server. You've got to install that locally on your phone using Cocoa or Android's SDK, and that's got the business logic also. It communicates with the web server using probably an HTTP connection, similar to the web browser's one. And so you've now got effectively a sort of client server-like, more intelligent, more lightweight version of that running here. So that's the application we'll deal today. So when you talk to developers and talk about the presentation tier could mean the stuff on the server that generates the page layout. It could be the widgets on the page that are being generated in the browser by the frameworks. Similarly, the business logic in terms of like validation and checking data, that could be done on the browser. It also could be repeated on the server. So be careful when you're talking to a developer, or if you are a developer, make sure you're clear with the tester which layer and on which is local, what's remote, where is it? Because some of this stuff is now repeated and distributed. So that's an overview of the sort of key elements of software architecture. So why this is important is typically, and I don't want to be too pigeonholing people, but testers and developers often see the system differently. Developers are building the system from the inside out, and testers, by their design, are often looking at the system from the outside in. How is the user going to experience it? How is the user going to find this application, and what errors are they going to run into? And so one of the things will be, if you look at those different tiers, and we have them here, here's our UI tier, our business logic tier, our data storage tier. A tester's first thing will be, well, what's covered by the test the developer has done? And I'm talking mainly here about the unit tests and maybe API tests, plus some automated UI tests. What's covered? And it depends on your application. You should talk to your developers, look at your architect or your product owner or scrum master. What is covered by our unit tests? What's covered by our API tests? What's automated? What, as a manual tester or an exploratory tester, as I'm coming into this, what do I not need to worry about so much because it's being covered? And so typically in a good modern system, you will have a large number of unit tests, which will cover, in theory, the business layer, and by proxy, most likely the data layer. And now that doesn't mean they cover it perfectly, does not mean they cover every exception case. They may only cover the happy path. They may only cover certain types of data, but the unit test should cover a relatively large amount of the business logic layer and the data storage layer, and should catch any catastrophic things that have happened in the latest update. You may also have API tests that will cover the APIs, which is really good. And I have another talk on API testing because APIs are effectively a contract with other systems. And if you break them, it can take out whole bunches of other downstream systems. API testing should be taken very seriously. UI testing, whether automated or manual, is a good thing. You should be able to automate some of it. But if we look now at the testing pyramid, this is the investment people will calculate. It's more expensive to test the UI than the service than the unit in that area. So it's a pyramid because the unit tests have got well-defined interfaces. The code, if it changes, it's easy to find the parameters that have changed. You don't change it very often, so any tests you do are going to be lasting. The API/service layer, same thing. Well understood contracts, well understood data formats. If a change is made, it's going to be understandable what the change is and doesn't change very often. The user interface changes all the time. Users have great preferences. Designers have preferences. You're trying to catch up with other companies that have changed their UI. There's a lot of trend setting on the internet where suddenly all apps look like Bootstrap. Suddenly all apps look like something different. So the UI tends to be the most changing layer and the least stable. And it's also the hardest to just automate by its very design. So typically, if you look at the testing pyramid, you tend to want to automate as much as possible of your unit tests and services. Only when there's time left, do that for the UI. What that means then, if you go back up, is there should be good coverage of your business layer and your API, but there's usually less coverage of your user interface. So when you're planning out, looking at the architecture and planning out testing, you should plan accordingly. Know that the UI is going to be less stable than the other elements. And if anything breaks in the UI, or even if you go back up one level further, if we consider the unit test and the API test to only be testing this lower gray box, there's quite a lot of business logic even in the UI. There's quite a lot of presentation logic in the UI, and those are probably not being tested by the unit tests. So business logic in the UI is often an area where things will go wrong quickly because people will make changes on the server, they fix them, they change some validation, they change some logic. It's all well and good, the unit tests pass, but then when you go to try and do it as a user, well, it doesn't work in the UI because something wasn't updated there properly, or updated was forgotten or missed altogether, and so it starts to break, thus giving you that often that disconnect where, but that code should work versus, oh, that code doesn't actually work. Because as a user, you have to use the system, you're using all these layers, and every single layer has to work for that one action for you to get a working experience. So as a developer, it's frustrating because you can spend, fix 99.999% of the problems, but if that 0.001% affects the presentation layer, or certainly affects that particular use that the person is doing, they'll see it broken. As far as they're concerned, it's all broken. It doesn't matter that 99.9% of the work to get to that point works. That last piece doesn't, and that's all they're going to see. Okay, so to expand upon that just a little bit, imagine we have this application here. We've got the business logic, we've got some components, 1, 2, 3, 4, 5, 6. We've got 3 screens, A, B, C, and the unit tests. As we've now said, in this case, the unit tests only test the business logic. They're not testing any of the screens. So the unit test will pass. The developer's like, yeah, this is great. We should be in good shape. When maybe there's some bugs in the UI we've got to fix, but the unit tests are all pretty good. So most of the system is good, but the unit tests pass. But suddenly, screens A, B, and C, none of them work. So the question is, wow, why is that? That feels really bad. Suddenly, the developer's like, well, all the components work, but the test is going to say, well, and the user will say, wow, all the screens don't work. So is the application broken or is the application working? And so what happens is, as a developer, you might fix a component. You may fix components 1, 3, 4, 5, and 6, but you left a bug or missed a bug in component 2. Well, component 2 is being used in screens A and C. So even though you fixed almost all the components, what the tester will find is that screens A and C don't work. And this is particularly frustrating if the developer forgets that component 2 is being used in screen C. Because so maybe what happened is a worst case. Let's say everything's working and the developer makes a change in component 2 and it causes screen A to fail. And the test is like, well, can you fix it? And the developer fixes it, but instead of just fixing it, breaks screen 3 because screen C, because the same component is being used in both places. So anytime you touch component 2, you're going to potentially break screen A and screen C. And if you fix something in screen A, you may forget to retest it for screen C, and it will break something there as a side effect. And the problem then is that as a tester, you then lose confidence, because what happens is as far as you're concerned, well, you told the developer to fix something which, as far as you're concerned, is in screen A. There's no relation to screen C at all, visibly. They don't use the same user interface. They're not in the same part of the application. They're in different part of the navigation tree. Now, behind the scenes, they are fully connected, and it's completely obvious that breaking something component 2 could easily affect screen A and screen C, but it's not obvious. So the problem is the tester doesn't understand why screen C out of the blue just stopped working. And now starts to feel like, oh, well, if screen C stopped working, there could be problems in B, D, E, F. And so it makes suddenly, it expands the scope of testing, and now you're retesting everything. And that's what we've seen a lot, where you can't articulate cleanly between the different members of the team why something broke. You then get the situation where you assume everything must be broken and you retest everything, and that delays your release months. So having these conversations around architecture and what's the connectivity of things, what's connected, what's not connected, really helps. Now, connected to this is also what I think is a very dangerous thing, which is refactoring. Before Agile, you would spend a lot of time up front designing a system, designing the architecture. You do a lot of work designing out all the different components, all the screens and everything, and you could spend months and months doing all this. The problem was, of course, if you've moved to Agile methodologies and you know why we do this now, is that the problem is that as soon as you start looking at the requirements and talking and building the system and talking to users, you suddenly realize that a lot of those designs just didn't hold water anymore. That is, things were different. As the users started to use the system, they realized that parts of the original design just wouldn't make sense. They would rather work a different way, and all that would get thrown out. So in the Agile world, we design enough architecture to do the initial components, the minimum viable product, the MVP. However, what that means is, as you start to grow a system and grow the functionality and add more things to it, the original architecture won't scale. It doesn't support everything you thought of, and you're adding things. So you may have, for example, in traditional software development, you would say, we're going to design all the common stuff first. We'll build the logging functionality, the error handling, data management. We'll build this really elaborate thing that does screen navigation and all this stuff. And you can spend months doing this. And I've seen systems that did that, where they would spend all this time building these common services which we're going to need, which we never needed. And the application took so long to get anything useful that it was canceled before it was ever built. So in the Agile world, we do the opposite. We just figure out what's the minimum necessary. But the problem with that is we then have to refactor the architecture. And that often means we'll do things like, well, these 10 screens all have to display error messages, and they all do it in 10 different ways. And if we have to change it, we've got to change it in 10 different places, which is bad. So what we'll do is we will come up with a generic logging system, a generic error handling system, things like that. And this is the most misunderstood part of it, because unfortunately, whenever you refactor something, it actually means you're making significant changes to the architecture. But the problem is, because those significant changes don't usually make the user interface change much, for the most part, people will assume, oh, the screens look identical, the application is the same. Therefore, there's not a lot of testing to be done, or the testing we surely couldn't have changed very much. And I think that's a very dangerous assumption. So, this is literally what we've had in some of our examples internally where we're building our applications, which is the developer will say something in a stand-up like, well, for today's meeting, for this sprint, I'm going to do some light refactoring. I'm going to be changing the error handling and the data management and the navigation service. I'm just consolidating some code that's in a bunch of different places. The screens will look the same. There might be some side effects, but I'm sure I've tested all those. And what they've really done is they've rewritten 95% of the application, or at least they've touched 95% of the application, because these core services are used everywhere. And if you've taken 100 pages and turned them into one generic logging service or error handling service, well, you've made changes to 100 pages that could now break, because those 100 pages might have done it slightly differently to each other. And that's probably been slightly forgotten or overlooked or simplified, or who knows. Certainly there could be issues. Doesn't mean there are, but there certainly could be. And so suddenly all those pages now might break in ways that the developer didn't fully appreciate. So really, whenever you're refactoring core services, understand how many pages, how many user functions, how many user stories, whatever you're measuring, do those core services affect, and make sure you understand, do you have time to test all of them? Because otherwise, maybe you shouldn't move every single page to a new logging service. Maybe you just change a couple of pages to it. And then every time you touch those pages or other pages, you do it on an as needed basis. So that means you won't have 100% generic functionality yet. It'll take you maybe 5 sprints to get there, but the risk is much lower, because if you break something, you'll break it on 3 pages, not 100. So that's an idea. Anyway, so That's an example, though, where we would have risk in our architecture. So refactoring can often generate significant risk. So here are some ideas I have of how you can identify risk in the architecture. And I'm doing another presentation at this event on risk management, and we're called Run the Risk. So if you want to learn more about risk, please take a look at that presentation. So one thing I would say is look for shared services up front. Things like logging, error handling, data management, web service, authentication, authorization, and there's a bunch of them. Things like that tend to be used across multiple different use cases across different parts of the application. And if they will fail not necessarily badly, but they will prevent anything that uses them from working. So it might take down 90% or 100% of the application. For example, if the authorization and authentication service is not available, you can't log in anywhere. If the error handling service breaks, probably anytime you get an error, you're going to get an unhandled error, which is then going to go into a loop and potentially use up all the system resources and cause the system to go down. These things have happened, things like that. So anytime there are core shared services, understand how wide they are, how widely they're used, and if they fail, will they fail safely? So for example, in our logging services, we often have it so that if a logging service throws an error, you don't log the error. Otherwise, you'd be creating an infinite loop. Similarly, error handling services should have error handling in them that if they fail quietly. Things like that. Nothing more frustrating for a tester when they try and test something and not only does the app break, which they expect sometimes, but the app itself completely stops working and they can't even get the error messages because the error handling broke. So shared services can be very dangerous for testers. It's very hard to know what's going on too. So if you get a failure, for example, in your error handling, and your error handling is being used in 3 of your components, well, and if your screens use your components, what was a one-line error in one error handling service might take out 100 pages, and a tester is going to try and use the application that morning, and they're going to see everything is broken, and they're going to lose confidence in the application. They're not going to understand why it suddenly broke. It's very hard for them to give value, and it creates a lot of frustration. Another area would be, so that's commonalities in the system, but the other thing is also user flow. Even though the login page is a standalone page, just as an example, there's nothing shared in the login page, it just lets you log in. And so from a technical standpoint, there is nothing about the login page that makes it a shared service, except that for almost every human user that logs in, you have to get through it first to get anywhere useful, unless the application is mostly outside of a login, outside of a paywall. But certainly for apps that require authentication to do most things, then a lot of times, if you can't log in, it's going to be a useless set of testing. So make sure you understand that, because first of all, if you do have a bug in the login page and it prevents you getting anywhere else in the application, you've now got an idle testing team who can't do very much, which is not going to make you very popular with the project management or with the people delivering the system. So make sure any page that have user flow bottlenecks are well tracked, and if an issue arises, which can obviously happen, get it fixed as soon as possible. Make sure you understand why it broke. Spend extra time on those key choke points from a user flow, because if you get a failure here, suddenly you can't get anywhere else. And the other thing I would say from a risk standpoint would be, look at where in your architecture lots of code has been committed recently. If everyone's been committing a lot of code into either one of the key services, or even just one of the business components, if you see a lot of commits there, you know that module is, even though the page might be all over the place, you could find out where are the commits, they go into this module, this module is used in 3 or 4 different places. Well, those 3 or 4 different places should be tested, or at least until it's stable. If you get an error here that's really bad, maybe you don't do these other 3 or 4 tests until we know that module is stabilized. So following the connectivity of the code and the relationships can be really important to know if something's connected or not. So speaking of connectivity and what's connected, is everything connected or is everything not connected? Oh, it depends. So let's give an example. So the tester, when they come in, they're going to come in here and they're going to look at an application. So in the example, which is a true example, where we changed some of the authentication functionality and some of the error handling functionality in this help desk application, what the tester experienced was that 99% of the pages did not load. Nothing would happen. Blank page or minimal bits, the nav bar would load, nothing else would load. And yet yesterday it had mostly worked fine. The developer had been asked to fix a couple of small bugs, and yet suddenly nothing is working. So this is a major regression. And as a tester, you're worried now, will we have time to test everything? We only have a few weeks left before the release date, et cetera, et cetera. We're in trouble. The developer's perspective was, well, as far as I know, I only made a small fix to a couple of lines to one small common data access component. And as far as I know, everything's fine. The unit test all passed, and this one service, it's a small fix. I can't imagine it would cause lots of problems. Which perspective is right? Well, the answer is they're both right, really. A small fix of one common component that's used in lots of places will create a small root cause to be fixed, but the symptoms will be massive and will be disruptive. And so if everyone's on the same page, if we understand architecture and the tester and developer are working together, they can go on a whiteboard or whatever method, or an online tool like Zoom, and they can go and start to look at it and go, okay, well, that failed there. That line of code has failed there. It talks to all these things. All these things failed. Let's go fix that now. Get that one thing fixed. The other bugs will hold off on. We'll get the build to do a rebuild, and then you can start testing again. The problem is if that communication does not exist, we get that situation in our very first story where, as far as the test is concerned, everything's now not working. The developers screwed up, and the developers doesn't understand what the big deal is, and that's unfortunately the root to a lot of miscommunication and frustration. So 2 case studies I thought would be helpful. We've talked about one already. One is our help desk tool. And this was the help desk tool released from hell, where we had, again, names have changed, Danny and Tina. In this, we had to do several important things, which unfortunately were very infrastructure heavy. We had to update the system to handle, to better improve security around cross-site scripting, cross-site request forgery, handling special characters and input validation. There was a lot of stuff we had to do in this release to really handle security. And it was done in a centralized way by changing a lot of the global settings, a lot of the global authentication, authorization, and also a lot of the modules that handle page data loading and filtering of data. So it was quite centralized and it affected every single page. And so we knew we had to do that. We also were making some changes to the help desk ticketing page, which was the core functionality so that the user would see. And so when we planned out this release, we figured, well, the help desk pages, we need to spend a lot of time getting those right and testing them and everything. And we're doing some small security updates, which are critical, but they're in this centralized one place. They won't affect a lot of things. And we're also doing some error handling to go with it. But what we ended up finding was, unfortunately, to fix the application to work with these new, more stringent settings required a lot of page rewrites. And so we ended up having to rewrite, 60 to 70% of the rest of the application because we had created side effects because of these security changes. And I think, so from an architecture standpoint, when we did the test planning, we didn't fully appreciate how much time it was going to take to redo all these pages. We probably, in retrospect, should have released some of the security updates more piecemeal. There were ways we could have done it in a way that would have been less invasive, but we didn't do that. And by the time we realized we were too far along in the changes. And so we just had to plan extra months. But it was a very frustrating release, a lot of wailing and gnashing to get this one out. And we learned a lot from that about really understanding, don't let a developer go off and just refactor stuff to improve security, even if it's important. Figure out what the security is and what's the least invasive way of making that fix that is secure but doesn't have side effects, and plan it out accordingly. So I think we misestimated what it would take. And then the second one was the opposite example, where we were changing the login page to handle single sign-on through Okta and other auth providers. And because of the pain we had on the help desk tool, and we had the same team doing the work, there was, I think, an assumption that, well, because we're changing single sign-on, which is authentication, and it's everything has to be logged in, everything that therefore could be broken because the login was going to change everything. And so we planned out this a large amount of work to test all these parts of the app that could be impacted by it. And in retrospect, if you actually look technically at the architecture, the single sign-on was not being implemented as a shared service. Because of our lessons learned on the development side, we actually were implementing it as a standalone login feature that once you were logged into the app, most of the shared services work the same way. And so actually we end up overestimating what it would take, which isn't a bad thing, but it meant we probably spent more time doing some testing we didn't need to do. We could have focused on other aspects of the application release. So in this case, because we, I think, overlearned the lesson previously and we didn't look critically at the architecture, we overestimated. So when you're looking at a set of architecture changes or refactoring, understanding what's changing, where it's changing, is it low? The lower down you change these in the stack, it's going to impact more things. If you change one thing on one page, however bad it is, it will probably only break the page. If you've changed something in the data access layer or in the business logic layer that's shared, or especially a shared service in the business layer, that and the data access layer are probably going to potentially break everything. So for example, we're right now looking at upgrading Microsoft Entity Framework 4 that we use to Entity Framework 6, which should be a very straightforward change, but we know that if it doesn't work, it's going to break absolutely everything in the application. The good news is we do have a lot of unit test coverage of those layers, so that will mitigate it. And that's a good idea. If you have a lot of changes to be made in those lower tiers where you can break more things, those are the tiers that can be better unit tested, thus reducing the amount of manual testing. Doesn't mean you shouldn't do manual testing and exploratory testing. You'll always find things, but at least you can improve your automated coverage. And with that, I'm going to wrap up today's talk. So just wanted to give a few takeaways. First of all, when you're focusing on testing, it's very easy to get into what I call a user story driven mindset. We've got these stories, we're going to test them, we're going to do some basic regression testing, we're going to be done. That's a very simplistic view. Make sure you understand the architecture. Look at what changed outside of user stories. Was there any refactoring goals? Were there any risks that were introduced into the architecture? Look at your architecture. That's number two. Look at your architecture critically. What's unit tested? What's other kinds of automated testing? Where is your test automated coverage the strongest? Where is your automated coverage the weakest? Look at the gaps in coverage and make sure you're going to have enough time for humans to fill those gaps as necessary. Make sure developers and testers and architects and other people, business analysts, communicate what the goals are for this release. Make sure you have common goals. That's the features you're going to release, but also what are the refactoring goals. In Agile, we should always have refactoring goals and do it every release as much as possible so you don't get technical debt built up. But make sure there's a common understanding of what that refactoring goal is, what's the likely impacts and side effects. And lastly, even if you do none of these things, at the very least, there's a common understanding of architecture. If your developers can teach your testers about architecture, and your testers can teach your developers the implications of the architecture, everyone's in a better place. You can have better conversations. Instead of I did this and you did that, it can be more about why did this happen? Let's understand how it happened. And that's always a better conversation to have. So with that, I will pass it on to any questions for this talk.